This lesson is all about the polar coordinate system. Up to this point, we have very exclusively used a rectangular coordinate system in order to describe the locations of points in a plane. It is possible, however, to use other systems to describe the location of points. One such system is the polar coordinate system, which locates points using a direction and a distance from the origin. So for instance, here is our familiar rectangular coordinate system. Any points that we want to locate, we can find using a pair of coordinates, x and y. So this point may be 6, 6, for instance. And you can uniquely define every single point, which is what's important in a system. But it's not the only system that exists. There's also the polar coordinate system, which uses a distance from the origin and a direction from the x-axis. So the x-axis is 0 degrees, and generally we have markings from multiples of 15 degrees all the way around the unit circle, basically. Okay, and if we want to locate a coordinate, we could just provide a direction and a distance. So this right here could be, for instance, 7:30. So there's a direction of 30 degrees. I'm on this 30-degree line, and I've come out 7 units. So 1, 2, 3, 4, 5, 6, 7. Okay. You can convert between the two sets of coordinate systems, and that occurs through our basic transformations that we've dealt with and learned all along. So x equals r cosine theta, y equals r sine theta, r squared is x squared plus y squared, and tangent theta is y over x. So for example, let's identify the quadrant that each of the following points lie in, then plot the point in the polar coordinate system. So point A, 345 degrees. So this is going to be in quadrant 1. And I know that because 45-degree angle measure is in quadrant 1. So I'm along the 45-degree line, which is this one, and I go out 3 units from the origin. So there's 1, 2, 3. So there's 345. And that's how you locate any of your points on the polar coordinate system. 7, 300 degrees. 300 is past 270, so that puts me in quadrant 4. And it's 30 degrees past that 270 degrees. So let me scroll down a bit. So this is my 300-degree line. So 1, 2, 3, 4, 5, 6, 7 units out. So this is 7, 300 degrees. The last point is 5, 270 degrees. So this is a quadrantal angle, so it's not technically on a or inside a quadrant. So I'll just write that it's quadrantal. Oh. Need an N in there for quadrantal. All right, so it's 270 degrees, which is right along this way, and then 5 units from the origin. So 1, 2, 3, 4, 5. So 5, 270 degrees. Notice that point is technically labeled with a -5. That's not really necessary in the polar coordinate system, although I do see a lot of polar coordinate systems labeled with negative numbers. So technically, you shouldn't have these labels on the polar coordinate grid. You should only have positive numbers that are labeling. And generally what I usually see is a polar coordinate system where only the positive x-axis is labeled, because this is 5, like all the way around the entire circle, so you don't need to kind of keep relabeling that point. So the -5, I know that a lot of textbooks even print that. It's not really necessary. well-formed polar coordinate has a positive value for its magnitude and an angle whose value is within the range of 0 to 360, or 0 to 2 pi, if you're doing radians. However, you can still plot these points that are outside of these ranges, but it could lead to having more than one set of coordinates that maps to the same location. So for example, let's plot the following coordinates on the grid. So here's my grid. First I want to plot -6, 120 degrees. So 120 degrees is going to be in quadrant 2, and if this is 90 degrees, then I'm 30 degrees past that, so this is 120 degrees right here. So starting from the origin, I need to go -6. So what that means is, instead of counting this direction, I count the other direction to go -6. So 1, 2, 3, 4, 5, 6. That point right there is -6, 120 degrees. But you may think that doesn't really make a whole lot of sense, because that's obviously not the 120 degree line. That's the 300 degree line. Well, it turns out that there's just multiple ways of expressing the same point in the polar coordinate system, if you allow for angle measures outside of the range of 0 to 360 and negative values on your radius. So that's why we say a well-formed point only has a positive radius and an angle between 0 and 360. So a better way of showing this point would be 6, 300 degrees. That would be a well-formed point. All right, 8, -225 degrees. This time the angle measure is negative. So if the angle measure is negative, we don't rotate this direction, we rotate this direction. So we go 225 degrees that way. So that's going to land us right here. So we would rotate around to this line right here. And then we would go 8 in the direction of that line. So 1, 2, 3, 4, 5, 6, 7, 8. So there's that point. That is 8, -225 degrees. But certainly a better way of expressing that point would be to express it as 8, and this would be 135 degrees, because we're 45 degrees past 90. So that's a better way of expressing that same point. All right, the next one is -4, -270 degrees. All right, so -270 degrees, we would rotate this way until we get to here. That would be my -270 degree line. And if we're going to -4 off of that, then we would go down 1, 2, 3, 4. So right there is -4, -270 degrees, which is much better expressed as just +4 and 270 degrees. So using well-formed points really helps things out. So give two different polar coordinates that map to the rectangular point -2 √2 and 2 √2. All right, so this particular point is in quadrant 2. And the reason that I know it's in quadrant 2, the x value is negative and the y value is positive. So when the x is negative and the y is positive, that puts us in quadrant 2. Now, we need to figure out r and theta for this. So the radius, we just take the square root of the squares of the x and y values added together. So if I take -2 √2 and square it, so negative 2 squared is 4. The square root of 2 squared is 2. So it's really 4 times 2, which is 8. So 2 root 2 squared would also be 8. So this is the square root of 16, which is 4. So the radius of this point is 4. So I'm somewhere on this circle right here, radius 4. Now, the next part here is where exactly do I lie on that point? So to figure that out, I need to do an arctangent of the y, so 2 root 2, over the x. So this is going to be arctangent of negative 1. The problem with arctangent, however, is that it's only going to return values that are either in quadrants 1 or quadrants 4. But I know that my point is in quadrant 2. So basically I'm going to get a reference angle here, and I'm going to need to change that reference angle into something that is, relative to the actual problem that I'm working. So arctangent of negative 1 is negative 45 degrees. So negative 45 degrees would be rotated this way, but that's not what I'm looking for. I am looking for something in quadrant 2. So here is the angle measure that I want, the 45 degree angle measure in quadrant 2. That's actually a 135 degree angle measure. So what that means is my point is 4 units out and on that line. So 4 135 degrees. So there's one way of expressing that particular point. But it said to find 2 ways. So 4 135 degrees. There's one. Let's find another. Well, we could use, if you'll notice, the negative 45 degree and the 135 degree are on the same line. So I could technically do negative 4 and negative 45 degrees. So that would rotate, the angle measure would rotate me to negative 45 degrees, but then I would start counting backwards, which would push me up to 135 degrees. Then there's actually all kinds of ways I could do this. Another way is to do an angle measure rotated all the way around in the negative direction. So if I rotate all the way around this way, that would be negative 225 degrees. So I could do 4 and negative 225 degrees. There's yet another way. There's lots of different things that I could do to come up with the coordinates of this point. They're not unique unless you have a well-formed point. Let's do some examples converting equations from either rectangular form into polar form or vice versa. Starting with x plus 2y equals 5. To do this, the things you have at your disposal are basically these. X equals r cosine theta, y equals r sine theta, r squared equals x squared plus y squared, and tangent theta equals y over x. So you're basically going to use those and change the equations over. Now, in polar form, we're trying to get into the form of r equals f of theta. So you have r by itself on one side of the equation and some function in terms of theta on the other side. If you can't get there, that's not too bad, but try your best to get to that form completely. So for instance here, I can change x into r cosine theta, and I can change y into r sine theta. So technically, I'm in polar form at this point. There's no x's or y's left. But I want to get it into that form where I have r on one side by itself and everything else in terms of theta on the other side. So if you'll notice, there's a common factor of r in both terms on the left-hand side. I'm going to factor that out. And now I can divide by that whole term, the whole term cosine theta plus 2 sine theta. Divide it over, and I get r equals 5 over cosine theta plus 2 sine theta. Now I have something of the form r equals a function of theta. So r's on its own, and only thing left on the other side are just things in terms of theta. Okay. X equals 2. So here, just change your x into r cosine theta. It's already a function that is polar, but you want to try and simplify it if you can. So in this case, if you just divide the cosine over, then you get the cosine to cancel, so r equals 2 over cosine theta. That's fine. Or you could also change this into 2 secant theta, and that's perfectly fine as well. Next, we have y equals -4. So y we can change into r sine theta, or do it as r equals -4 over sine theta, or -4 cosecant theta. So a lot of these just come down to changing your x and y's into r cosine theta and r sine theta. But you can do more advanced transformations, like you could change x and y into r cosine theta and r sine theta here. But we also know that x squared plus y squared goes directly into r squared. So this becomes r squared equals 36, or if we take the square root of both sides, we get r equals the plus or minus square root of 36, which is just 6. And it turns out that because we want to only deal with well-formed points, we can generally only have to worry about a positive radius in this case. It's a little bit, there's a little bit more nuance to it, but in general you can do that. Going the other direction, let's convert this first polar equation into rectangular form. So essentially what you're looking for is a factor of r sine theta that you can change into y, or a factor of r cosine theta that you can change into x. Now don't exactly have that. There's a couple things we can do, however. Since we know that y is r sine theta, we could divide both sides of this equation by r and say y over r is just sine theta. So I could make this r equals 3 times y over r. Now if I multiply both sides of the equation by r, I get r squared equals 3y, and then r squared can be changed into x squared plus y squared. And generally these, as long as you get them in rectangular form, so everything has x's and y's, you can generally stop at that point, because there's not a lot of times where you can actually get these into just y equals some function of x. So next here, r equals 1 over 1 minus 2 cosine theta. So let's see what we can do here. I will start off multiplying both sides by the denominator. So I'll have r times 1 minus 2 cosine theta equals 1. And then if I distribute the r into the set of parentheses, I get r minus 2r cosine theta equals 1. R I can change into the square root of x squared plus y squared if I like. But r cosine theta I can make just an x. So I end up with here the square root of x squared plus y squared equals 1 plus 2x. Or if you want to get rid of the square root to make it look a little bit nicer, that's fine, although it's not really necessary. Then just square both sides of the equation. And I'm sure if you multiplied this binomial out, you could combine terms and whatnot, but that's probably about as far as you really need to take it. All right, this next one. So, similar technique to what we did in the first example. I can change cosine theta into x divided by r and sine theta into y divided by r. Now, if I multiply both sides of this equation by r, I'm going to have r squared on the left-hand side equals negative 6x minus 3y, or x squared plus y squared equals negative 6x minus 3y. And again, I probably could get that to polish up a little bit nicer, but in a lot of these, there really is no say as to how far you should really take it. As long as it's in rectangular form, meaning that you just have x's and y's left, you're going to be fine. For part D, r equals 2 cosecant theta. Well, just remember that cosecant theta can be written as 1 over sine theta. So this is essentially r equals 2 over sine theta. So if you multiply both sides by sine theta, you get r sine theta equals 2, or y equals 2. And one last example. R equals 3 over 2 cosine theta plus sine theta. So I'm going to multiply both sides by the denominator. And distribute the r. So 2r cosine theta plus r sine theta equals 3. So 2x plus y equals 3. And that's a nice equation of a line. Last up, we're going to look at doing some graphing of polar equations on the calculator. So let me pull up the calculator and show you how you get started here. So the thing about this is you'll have a y equals is always expecting some function of x. So if you want to graph something that's in terms of polar equations, you need an r and a theta. Well, the calculator can do this, but you have to go under your mode settings. And it's probably best that you stay in radians, although it's not really necessary, but generally it's a good habit to be in. And the next item down says function PAR, which stands for parametric, and POL, which stands for polar. If you select POL and then go to y equals, now notice your y1, y2, and so forth have changed into r1, r2, and so forth. And if you hit this variable key, you get a theta instead of an x. So it's ready to do equations for you, to compute and graph equations in polar form rather than in rectangular form. So for instance, let's say we want to graph r equals 2 cosine theta. So I would put in the calculator 2 cosine theta. One thing you want to be careful of is to always check your window. Generally, you want your window going from 0 to 2 pi. And if you're not sure what 2 pi is, you can actually just type in 2 pi, and then it'll compute it and put that down. Theta step. This is how often you want to compute values of theta. You know, multiples of 15 degrees is usually good. What I'd tend to do is just put in like pi over 12 or something like that. And that's usually fine. The smaller that is, the better picture you're going to get, but also the longer it's going to take to draw. X min, X max, X scale, these are the same as they were before. And I'm going to change into -5 to +5 on the X and Y. And I think that'll be fine. So when I graph, I get an oval looking object here. But it turns out that the graph of this is not an oval. It's actually a circle. It just looks like an oval because there's more pixels in the X direction of my screen than there is in the Y. So if you hit zoom and go down to zoom square, what it will do is it'll adjust your X values so that they take into account that differing number of pixels on the X-axis as there is in the Y. And then you can see, you know, that it really is a circle. If I go and change my window, kind of zoom in on it, oops. Zoom in on it, so this would be, let's say I want to go from like, you know, -3 to +3 on the X and Y axis instead. Now notice my X has been changed to, it's different from -5 to +5. That's fine. I'm going to leave that there, and I'm going to let the calculator come up with the X and Y's. I'm sorry, the X's based on my Y's. Theta step, I'm going to leave that as it is. It's pi over 12. And then I'm going to go to zoom and square, and it will go ahead and adjust those X and Y pixels accordingly. And so there's my graph, a little bit more zoomed in. Now, let's try a different one. R equals 2 minus 3 sine theta. So I'm going to do 2 minus 3 sine theta. And graph. All right, that's what this new graph looks like. One thing that I do want to try and show you if I can, if I go under the window and change the theta step, like let's say I change it to, right now it's pi over 12, I'm going to change it to pi over, say, 100. So it takes a lot more time to graph because it's calculating, you know, a lot more points to plot. But it's going to look a lot more curved than it did when it was, you know, just pi over 12. And certainly if you went less than pi over 12, then it would look very non-curvy. It'll look more like straight lines. So let's say if I do like pi over 6. So you can see it almost looks like a polygon. So what it's doing is it's calculating a point at every pi over 6 and then plotting those points and connecting with lines. So the larger density you use, the better image you're going to get, but the longer it takes to graph. Okay, R equals 4. And let's go with, Y equals, so just R equals 4. And I'm going to change the window so that it's calculating some more points here. So I'll do pi over 24. So pi over 4, it is a circle, although it doesn't really look quite circular. It's probably because I just didn't get enough points, but I thought pi over 4 would, or pi over 24 would get me a good picture. Let's change it. There we go. So pi over 100. I'm getting a much nicer looking circle here. But again, it's taken a lot longer to draw it. If you'll notice, that graphed from zero to 2 pi. Let me show you one other situation you could run into. Let's go back to 2 cosine theta. All right, when I graph this, I'm going to do it nice and slow. Let it graph. Notice that it's still thinking, it's still doing something. But it's not really giving us any more graph. So what's happening is occasionally you can get a graph that actually goes through its entire cycle from 0 to pi or 0 to something less than 2 pi. So if I change this from 0 to pi and graph, I still get the entire picture, but I don't get that, calculator thinking and drawing the basically the overlap. So some things you have to kind of consider in polar graphs. That sort of thing can occur. And it's generally not a problem, but you do have to be aware that it exists. All right, one last one here. R equals 0.2 theta. So I'm going to go into y equals, and change to 0.2 times theta. Then my window, I'm going to make my theta step a little bit larger here. And leave the rest for now. Just see what happens. Not a lot, huh? Well, let's see what happens if I play with some settings here. So I'm going to go back into window. This is down to just pi. Let's see if I make this back to 2 pi, if that affects my picture. Maybe this isn't drawing the full graph in terms of pi. Okay, now we're seeing a little bit more, but maybe this isn't the entire graph. So maybe we kind of go out a little bit further. So let's go out to 4 pi and graph that. So we're seeing that same spiral, but now we get another loop of the spiral basically. So this is a graph of what's called Archimedes spiral, and you can actually continue to increase your theta max to basically infinity, and you're still going to continue to get spirals all the way out. So this should fill up our window at least. And so no matter what you set your max at, it's just gonna keep spiraling outward. And that's called our Archimedes spiral. Yeah, it filled out an entire window. So anyway, that is some different types of graph. Certainly if you're interested, you can look in the textbook. There is a lot of different graphs that you can do with polar coordinates that end up being very interesting. We really just kind of scratched the surface with the possibilities here. So if you're interested, look into your textbook, see what's out there and available, and try some on your own.